The Peck Lecture is named in honor of the late Professor Ralph B. Peck. It's delivered annually by a geotechnical engineer selected for outstanding contributions to the profession through the analysis and publication of case histories. The 2014 Peck Lecture is Professor Youssef Hashash. Professor Hashash obtained his BS, MS, and PhD degrees in civil engineering from MIT. After completing his studies there in 1992, he joined Parsons Brinkerhoff's Geotechnical Underground Engineering Group and worked on tunneling and deep excavation projects throughout the U.S. and Canada, including some time on the superconducting supercollider in Texas. In 1998, he left PB and joined the University of Illinois, where he currently serves as professor and the John Burkett Webb Endowed Faculty Scholar. His research and teaching interests include underground construction and deep excavations, geotechnical earthquake engineering and seismic site response, numerical modeling and the use of visualization and virtual reality techniques in geotechnical engineering applications. Professor Hashash has made significant contributions to the geoprofession through his approach to the concept of case studies. He combines three important elements: design and prediction, real-time precise monitoring of performance, and a thorough study of how the results compare with predictions. He's authored more than 170 journal and conference publications, and he holds multiple patents. He's a Beckman Fellow at the Center for Advanced Studies at the University of Illinois, and is a recipient of the Presidential Early Career Award for Scientists and Engineers, as well as a Casa Grande Award, the Crows Medal, and the Middlebrooks Award. Professor Hashash, would you please join me on the podium? Professor Hashash, I'm very pleased to present to you the 2014 Ralph B. Peck Award.
Thank you very much for the kind introduction and for this wonderful honor, and I'm actually quite impressed by the audience that we have here today. I'm going to be talking to you about a number of contributions we have made over the past, I was counting, 22 years, from my PhD through my practice and also during my research over the last 16 years at the University of Illinois. And the work that I will be talking about today is something that really is a team effort. In fact, multiple teams from multiple groups that have contributed to this work, and I'm very much indebted to them for many of the items I will be describing to you today. I'll highlight the National Science Foundation and Dr. Rick Frugese. You know, you need this funding to be able to explore ideas that sometimes may seem to be a little bit out there. I had many colleagues and collaborators from Illinois, Professor Rich Finno, who has been a long-time collaborator and friend, Professor O'Rourke, colleagues at Clemson, Dimitrios Kotsoftas, Schnabel Foundation Company, ARUP, and then various colleagues there, Geo-Instruments, UC Berkeley, Professors Moss, Cox, Kahan, Dr. Kahan, other institutions as well, many graduate students, and you know who you are, and you know that's the many nights that you've spent trying to make the work work. Of course, my PhD committee at MIT, Professor Whittle, the late Professor Whitman, Professor Ladd, who's with us here today, many friends and colleagues, people at Parsons Brinkerhoff, and the Geo-Institute and the Earth Retaining Structures Committee. I will first start with an introduction, motivation, what's the problem, what it is we're trying to go after. Then I'm going to describe three themes, three key technologies that I would like us to discuss. Acquiring a construction record via imaging technologies and social media. For the young in the audience, there's some for you there as well. And think of the construction record as the action, the cause. And then we have ground and infrastructure response monitoring via network instrumentation and sensors, and this is the reaction of the ground to our excavation activities in urban areas. And then we bring those two together, and this is where we talk about modeling and estimation of ground response via self-learning algorithms. And then I'll have some concluding remarks. Now, it's quite fitting to start the motivation for this work by the pioneering work of Dr. Peck and his work on the Chicago subway, where he represented Carl Terzaghi, all things Carl Terzaghi had to communicate and consult on for the project. And there they really highlighted the importance of the relationship between excavation support, construction sequence, and deformations and impact on surrounding structures. And that led to the birth of the observational method. For those of you who may not know where Dr. Peck is in this picture, he's actually here. This is Dr. Peck, and also here in this image. And this is an image down here of the Chicago subway activity. Going along with the theme of this conference on sustainability, underground urban space is essential for having sustainable cities. It will allow us to put many of our infrastructure below ground and enhance the living environment. An excellent example would be the Boston Big Dig. This is, in fact, where I first learned about deep excavations and the garage at Post Office Square. And here what you're seeing is a picture of before and after the construction of the Central Artery project. Once you place this highway underground, we were able to reunite the city. It changed the fabric of the city. Now, I do recognize there are many issues and controversies associated with the Central Artery, but let's put these aside for now. We continue to be interested in exploiting underground space throughout the country. It is really a hot area. Underground construction is really interesting and challenging in my opinion. Here I'm going to talk to you, describe to you a project in San Francisco. It's called the Trans-Bay Transit Center, which is designed to house what people are calling Grand Central Station of the West. It's a massive excavation, 1,500 foot long, 180 feet wide, and 60 feet deep in soft to medium clays in a heavily built environment. So we want to develop that without shutting down the city, and also without damaging our adjacent structures. So as engineers, if we want to look at this, the process or the issues and the concerns that we have in a simplified fashion, we want to build an underground space. So we install our wall, we pre-install those walls, and we start excavating and installing our bracing system. And with that, because we are unloading, we are removing soil and reducing stresses, there's going to be a reaction, the ground will move, and we will have some wall deflections. Now, these deformations will propagate through the soil and manifest themselves in terms of surface settlements and lateral deformations towards the excavation. Now, if these are excessive, then what we're going to have will be potentially damage to our infrastructure, cracking of our buildings, damaging the utilities. And our challenge as engineers is to develop this underground space efficiently with minimal disruption. It cannot be zero. And this is actually many of you who probably practice in this area, when you go and ask the third-party owners, so how much deformation can your structure tolerate? Say, 0. Well, we know that cannot happen. So we are going beyond just simply looking at failure for these type of excavations. We are interested in keeping our deformations small. So we need in our engineering to estimate the behavior. We want to control our construction, and we want to be able to be flexible, adjust and update. And so what I'm going to talk about are a number of tools that will help us support the observational method. So our objective is to develop the space economically. You want to try to control cost, but also you want to minimize the impact on existing infrastructure, and there's a tension between those two requirements. We want to have some estimate of the deformations ahead of time, the impact. We have to, of course, do a very good and detailed field and laboratory investigation program. Then we develop our design, and we go out for construction. We want to keep track of that, and we really need to have a very good record, because we know the deformations are quite sensitive to these, to the particulars of the construction activity. Then we have field data monitoring, where we put our instrumentation and we see the response of the ground. We want to put that in a way that is presentable to us as engineers, and then we compare that with our initial estimates often enough they will be different. We want to understand the differences. We want to be able to update our models, and learn from these observations, and then potentially make adjustments to the construction sequence, to the design, or potentially do nothing and just say everything is okay. So we've been working extensively on this loop, and I will be spending quite a bit of time talking about the construction record, field data, and the update of our models. So why are we interested in this level of detail? This is really an excellent chart that is widely used for the estimate of deformations due to urban excavations by Clough and O'Rourke in 1990. On the vertical axis, you have the normalized maximum wall deflections that you can expect, and on the horizontal axis, you have a proxy for the stiffness of the bracing system that you are placed, and we have here lines corresponding to a given factor of safety against basal heave. And in our urban areas, and because of the constraints we have on the amount of deformations we can have, we like to keep our deformations within a fairly narrow zone, and they are going to be quite sensitive to our construction activity. So we need to know we need to control for the construction process, but also we need to keep track of it. We also need a fairly comprehensive monitoring program, a fairly detailed monitoring program. And then we want to use those cause and effect, that cause and effect information to develop higher fidelity models, because our structures are so sensitive to these type of deformations. Now, we'll start with the record of construction activity, and for many of you who've also been working in this field, you know that this is actually an issue. You have the resident engineers probably developing sketches of what's going on, probably not sufficiently detailed and sometimes inaccessible. We want a record that is accessible to the engineers, readily accessible, and that is has a high level of fidelity in that. And for that, we want to be able to capture the geometry, the change, where are the berms, when the struts were installed, or the tiebacks. So I'm going to discuss 4 technologies: laser scanning, image reasoning, 1-2-3D catch, and a BIM type of capabilities, SketchUp, to develop our geometric models. But not everything can be captured via imaging. We want to have a certain record of information of what's going on in terms of activities. And I'm going to describe to you how Twitter is being used to actually capture that valuable information. And of course, we have our quantitative monitoring of deformations, of pore pressures, that will allow us to complete the picture. So let us start with 3D laser scanning. Some of you might know it as LiDAR, and this stands for light detection and ranging. And it's a principle of pulse time of flight. You send out a laser impulse, and in a particular direction, you time the return of that impulse, and you can calculate the distance. And if you do that many, many, many times, you're going to actually capture geometry. So we did this work in 2004. You're looking at a machine at that time cost us at around $150,000 or so. And we wanted to see, would it work? It's actually never been done at that time. And I think Professor Daniel remembers this discussion about that when he was at the University of Illinois. And we wanted to explore, does it work in a practical fashion? Can I use it? So in collaboration with Professor Fino, there was an excavation literally in his backyard that we had access to, and we can try all of that. Notice we started in January 30th, 2004. And we needed to see how are we going to execute this campaign. This is a line-of-sight technology, so you have to have access, you have to have visual access to your site. So you need multiple points where you can station your laser scanner. And our laser scanner at the time had a 40-degree by 40-degree window. Nowadays, you can have them 360 by 360 almost. So that we needed to do multiple scans, and at multiple points. And then we compile all of those into a 3D model, a 360-degree model to scale. The thing we discovered is you do not need to be at the exact same points every time you do the scanning, and that's important because you know of issues of accessibility on an active construction site. So that was quite helpful that we could do that. We did the work about once a week. We would send out the students. We spent about half a day doing that. I think if you can see the temperatures, they didn't call it the polar vortex at the time, but it was quite cold. -5 degrees, minus 25 degrees with wind chill. And you know, this was a good way of testing whether this thing will work. So we put heating blankets on the laser scanner, heating blankets on the laptop, and we had a generator. And our students, whenever they were cold, they just took a run around the site, got warmed up, and then continued the work. So you do that, and then what can we do with this? So you start with these individual scans, and then you have to stitch them. You have to develop an appropriate coordinate system. And slowly you end up having a beautiful image, I mean, looks really nice, of the excavation, 3-dimensional to scale within an accuracy of around 5 millimeters. So it's good for geometry, it's not good for deformations, this particular technology. Now, you can do a lot of things with this image. You can clean it up. You can, and it'll actually scan everything inside. So it scans trees, buildings, people, excavation equipment. If you see here, for example, the excavator was moving. But what you have is a very nice image of your berms, which we know are important for estimating the deformations and doing our numerical analyses. So we can clean this up so we can focus on our excavation, take out the excavator, take out our bracing system, and we have a very nice surface that we have a very good geometry of that surface. It's very hard to send down surveyors into an active excavation. It's costly. It takes time. They get in the way of equipment. It's dangerous. So now I can remotely do all of that, acquire that information. I can take cross-sections of the site, and I can estimate where I am in terms of what layers I'm removing and how I'm moving the soil around, where my bracing is. And I can have develop some really cool stuff. This is actually a fly-through this. You're looking at 2-scale image of a 3-dimensional model of the excavation. We can get the positions of everything at the site, sizes of whalers, the geometry, and a level of resolution and fidelity that we've never been able to capture in our excavations. So really, it proved to be a successful. It was a time-consuming effort. There's a fair amount of work you have to do out in the field, as well as processing back in the back office. Now, we could do that, and we did that once a week. But when construction is going on, there are some important activities going on in between. And you sometimes need to know what's going on a daily basis, because it affects what kind of your interpretation of monitoring data, which I'll talk about in a little bit. We're able to get it in an almost continuous fashion. So if we think of our laser scans as sort of a boundary condition of a problem, we decided to explore the use of webcams as tools to look at what's happening in the interim. We can set up these webcams. We can program them to take pictures as often as we want. On the project site, we did it once an hour. But you can end up with a lot of images. And if you were to go manually through those images and try to figure out what's going on, again, you won't have a lot of time to do that. So we wanted to see, are there techniques, are there ways where we can go through this information, process them in an automated fashion to highlight the changes. And that brought us into a realm of image reasoning. Of course, it's all enabled because we're using digital technology, digital images, and we have a spatial matrix. And numerically, we can represent the pixels and the colors. The challenge for us was when you look at excavation surfaces, these are low-intensity, contrast type of surfaces, and just simply is doing a comparison between two images is not going to let us find out what's going on or detect that in an automated fashion. And this is when I was introduced by one of our students who really knew, went out of his way to look into these technologies, concepts of we call morphological operators, whereby you do something called dilation of an image or erosion, and then you can do an opening and closing of an image. And I won't go into exactly how you do that, but these are things you can do, manipulate a digital image that way. And then also we looked at how you take an image, it's negative, and when you add these two together, you end up with white space. So we took advantage of that. And then the clever thing in this process is you take two images at two different stages of excavation. We had to try it, of course, in our labs before we went out to the field. You take an image, you get its negative, and then you close it. You take an image of a later stage and you open it, and then you add those two images up, and what you left with is the contrast of where the changes happened at your site. And then you superimpose that on an image of the site, and you can see automatically where the changes happen. So this way you can process large volumes of images to pinpoint where the changes happened. In order to do that, we actually used Block 37 in Chicago, again in collaboration with Professor Finno. We had 2 days, August 8 and 9 of 2006, and at the time that camera was actually a low-resolution camera. We ran it through that process, and it captured that for us. Well, you'd say, you know, we have really nice techniques, good techniques that will allow us to capture this construction record, but we really were not satisfied. It's expensive to get a laser scanner. It's cheaper now, but it's still expensive. It is time-consuming and resource-consuming. So we looked at, well, you know, how about if we, you know, if I have my phone, has a camera, and I go inside the site, and I start taking pictures. Can I develop a 3D model of that? Well, if you're familiar with the principles of digital photogrammetry, we can do that, but you have to be at a particular location, particular distances. Your cameras have to be at a certain offset. We wanted something more practical. You're going down the stairs, down an excavation, you stop, take some pictures. Can I do that? Well, thanks to collaboration with Stephen McLandrich at Arup, we found this really fantastic software called Catch. It's freely available, whereby it will allow you to develop 3D models from closely spaced photos, but you do not have to strictly adhere to principles of digital photogrammetry. Well, we tried it on the Bay Transit Center in San Francisco, and this is some of the excavation work going on there with the bracing and the berms that are on site. And so we went there and we took those images, we fed them through the software 123D Catch, and we ended up with this three-dimensional model of the excavation. You can see the berms, you can see the struts, you can see also a little bit that I have some incomplete images, say, of the struts. And that's because it's also a line-of-sight technology, I need to have coverage that way as well vertically. So keep that in mind, because at the end of this talk, I'm going to tell you a potential solution to this limitation. But also look at the promise of this technology. I use my phone or a better camera, a nice digital camera. Okay, what? Even if you get a really good one, maybe I can get a $1,000 camera. I can do it with a $200 camera. And I use a free software, and I can get now a 3D image versus a $150,000 investment that I would need to make with a laser scanner. So really, this is a tremendous development, and this is something happened just in the last 14, 15 years of research in this area. So we can really do things that we couldn't think about before. The things we're still tackling right now is how can I get dimensions out of these 3D images or videos, and we're working on that. Now, another things we wanted to look at is how do we keep track of excavation activities, whereby you do have the engineers keep developing these hand sketches, and we wanted something that is, again, accessible. I don't need a major platform, something that engineers can run on their PCs, students can do in the office at the university. So we were using this software SketchUp, whereby we took some of the hand records from the engineers, programmed them in the software, and what we were able to do also is to develop an animation, a three-dimensional model that will show us the progress of construction. We're able to match it with a date timeline. We can show the installation of the wailers, the bracing, and then the development of the berms. And this is using a relatively inexpensive, off-the-shelf software. And then I can take this three-dimensional model and then use it in my analysis. I need that to keep that record in one place. Notice there I'm also using a digital record now, as opposed to just having sketches on a piece of paper. Now, not everything at a site can be seen. So if you're installing piles, it's happening below ground. So how do I keep track of that? Now, on the Bay Transit Center, the engineers came with an idea of, well, why don't we use an existing platform, Twitter? And many of the younger people are quite comfortable with these technologies and says, okay, why don't we tweet these various activities? And so this way you don't need a cumbersome procedure to keep track of things. And moreover, because they were doing the operations sometimes 24/7, the engineers, even when they're going to sleep, they can quickly check what kind of issues there are, what kind of progress we have. And so then we had access to that, we could see them live, but more importantly, we were able to mine this data afterwards to develop, for example, the construction sequence of one of the shafts. Coincidentally there on the project, actually, and due to a very attentive crane operator, they found a woolly mammoth tooth at the bottom of one of these shafts. They were grabbing these with a clamshell bucket, and they were dumping it, and the person saw it, and it's now, I think, at the California Academy of Sciences. So we have a number of technologies that are available to us to help us, to facilitate for us the capturing of this construction activity, which represents the action. So now let us move on to see how we're going to measure the reaction of our ground, how the ground is responding. The last 15 years saw tremendous development in automated and remote sensing. Most notably, for example, automated total stations, which we can have then targets all around a site, and then automatically, sometimes on the hour, just measure deformations of buildings, of ground surface. We also seen a lot of developments in in-place inclinometers, extensometers, piezometers, stills meters, strain gauges, and our ability to network these via wires or wirelessly. And really the wireless networking has been quite beneficial to us because we don't have to worry about stringing lines, which would be then exposed to damage, or having to wire antennas and then deal with power supply issues. So using even cellular wireless technology, we're able to now capture that data from fairly close to the source and allow us to have almost near real-time access. Now, I should mention that while we have made a lot of advancement in terms of real-time and in-place monitoring, we still have significant challenges. For example, we find that through the use of MEM technologies, that these sensors sometimes go haywire on us. And we need significant developments so that this technology would last us for the 3-year duration of a project. And I will talk a little bit more about some of our needs in this area. So let me illustrate to you some of the technologies we have. So for example, this is a total station, and then this is a wireless antenna that will allow you to receive that information. So you can, nowadays, on your smartphone, see what's going on at your site at any time of the day. Here also I'm showing you the webcam that was available to us. This is the total station on the Bay Transit Center project, and the targets were installed on the wellheads for inclinometers, which also doubled, by the way, as antennas for the wireless network. So that was really a very nice development and innovation. Just again for illustration, we have other kind of techniques we have as, instruments. We have inclinometers, extensometers, piezometers. We introduced there the use of flushable piezometers to try to observe the development of, potential development of negative pore pressure under the footprint of the excavation, and as well as significant instrumentation of the struts there. Now you can get this information. I'll show you a typical sort of set of data you get. So from the record of construction, we know what has been happening in the excavation, and then we can then match it with our observations, say, of piezometers on the Transbay. This is for the Transbay Transit Center. This is just simply really for illustration of what you can do with this fairly continuous stream of data. Now, we're looking at now multiple streams of data, and one of the things we run into, we've had prior experience with, is that sometimes the data is not warehoused in the same location. Sometimes in certain projects you find your calibration data is in one place and the actual measurements in another, and good luck trying to actually match them up or find them. So we looked at how we can use the concept of data warehouse to combine fairly heterogeneous data sets, image data, numerical data, different types of data, constant versus varying data that require timestamp. And for that, we actually looked at using a GIS framework as a sort of in the background to house all that data and tag it with appropriate metadata. And on the front end, you just have a fairly friendly user interface that will allow you to access any instrument and will allow you to pull up the data as well as plot that data that was measured for that instrument. You can also look at the geometry of the excavation. This we did for our research activity, but also we've seen it now employed in a number of projects, including the Transbay Transit Center, and there it's called a global analyzer. You open up this web page, you can select any instrument, and you can get a record with that. Now there are challenges with this, because sometimes you need to reset your instruments, and you cannot just simply expect it to just go on its own, work for it by itself without any additional interface with the data. So now what can we do? Why do we want this fairly continuous stream of data? Of course, we needed to make sure our third parties are not adversely affected, but also we can have some better interpretations and understandings of the engineering behavior. So for example, this is an illustration of data we obtained from the Central Artery project. We had a wealth of data on the strain gauges on struts, and we wanted to understand the behavior of these struts and the impact of the thermal load, which is an important element in interpreting the loads in these struts. And we found there, because we had such high resolution data, that the coefficient M, which represents the change in load over the change of temperature, is construction stage dependent. Up to that time when we published this, we were using a single value for this coefficient to separate thermal loads from earth loads. We find that actually it is construction stage dependent, and therefore we can have a better resolution of our information that way. So now we have technologies to capture the cause, the excavation, the construction sequence. We have technologies to capture the reaction, the data. We put those together. We have now a cause and effect, and so therefore we need to talk about modeling. And this is where I'm going to talk about small is beautiful. The importance of small strain nonlinearity in interpreting and estimating ground deformations. Berland in '89 recognized that. It's actually the title of his ranking lecture. And this is an illustration of the importance of the soil model you work with. Think of this as a model that does not incorporate the very small strain nonlinearity variation in the soil. And this is a model that does incorporate that, and the model that does incorporate that better captures the surface settlements that are very important for us in the excavation problem. The work I've done with Professor Whittle at MIT also highlighted this, the important the importance of small strain nonlinearity formulations in our models. I know Professor Stokey had to leave. He apologized he couldn't be here, but I think he'll be quite thrilled to me to state that VS is really a fundamental geotechnical parameter, not only for dynamic problems, but also for static problems, VS being the shear wave velocity of the soil. And it's something that we want to measure, and we want to measure reliably on our sites to be able to get this initial maximum modulus. This is where you start your nonlinearity. Moreover, we need to have better tools to characterize the soil behavior in terms of our laboratory testing at small strains as well. Now, over the years, we've seen acceptance by the profession of the importance of small strain nonlinearity, and you can find it in commercial software, for example, such as Plaxis. And this here is actually some of the shear wave velocity measurements that were done by Professor Moss, Dr. Kane, and Professor Cox at the Bay Transit Center, whereby we're looking forward to actually publishing some results of the impact of excavation on shear wave velocity of soil. Now, what can we do with all this data? Well, we can develop empirical relationships or semi-empirical relationships where you combine your data with some additional modeling to parameterize that. And we've done that in collaboration with Professor Huang and his students at Clemson. And we come up with some empirical correlations whereby we can develop initial estimates of surface displacements and also damage index or potential damage of adjacent structures. So that's one way we can utilize the data. I will not go into the details of these models, but there are also other uses of these data, which is learning from that. We talk about learning as engineers from experience, from data. And the question for us is, can our models learn? And I think sometimes the answer would be no, based on our experiences, but I'd like to hopefully convince you that actually we can do it otherwise. We know that there is a strong relationship between the soil model and the displacement around an excavation. So that's actually an important clue for us. That strong relationship means that there is a potential for using inverse analysis type techniques. This is whereby you use your boundary measurements to infer the soil behavior. Now, there are two classes of inverse analysis techniques that I'd like to talk about today. One is parameter optimization. So you have a soil model, let's say a hardening soil model or an MIT E3 model, for example. You have a set of parameters, and then you change them, adjust them using certain rules and logic, and so that you can minimize the error between the estimates from the model and the observations. So that's one type. Now, the issue with this type of parameter optimization is that you are going to always be limited by the quality of your soil model. So if it doesn't have, for example, anisotropy, no matter how much you optimize this model, it does not have anisotropy. If it doesn't have small strain nonlinearity, the same thing. But on the other hand, it is readily available using within a commercial software framework, so it's easier to use. Now, there are another class of type of simulations that we can work with, which these are called self-learning simulations, and I've been developing these over most of my career at Illinois, whereby we allow the soil behavior to change, to evolve with the data. You can learn new soil behaviors, such as anisotropy and small strain nonlinearity, but it requires greater hand-holding, let's call it that way. So I'm going to focus on the work on inverse analysis with self-learning simulations. So I have my field measurements, both geometry and response. And so instead of doing a single analysis and then keep on changing parameters, I'm going to run two analyses in parallel. In the first analysis, I'm going to impose my construction sequence, the geometry, the action. And due to equilibrium considerations, I'm going to stipulate that my stress field represents fairly well the actual stress field that is in the soil. And I'm going to extract that at my material points, integration points. I'm going to run a parallel analysis, and I'm going to impose my response, my deformations. And because of compatibility considerations, I'm going to say that the strains within that domain are a reasonable approximation of the strains in the field, but probably the stresses are not. So from one analysis, I have stresses. From another analysis, I have strains. Stress, strain, soil behavior, right? Now, in order to benefit from this information, I need a model that I can adjust along the way to be able to adjust to these stress-strain relationships. If I use conventional models, I have to, every time, send a student for 3 years to develop a new constitutive model and come back. So you can see that iterative process can take a while. So what I need is a flexible model that will actually learn on the fly. And instead of, I need to use a model that can adapt. And this is where we use neural network material model. But hold on, I know some of you may have said, okay, there he goes. These are models that can learn, can adapt. And you would initialize them to represent, say, elastic response over a narrow strain range. So, and then from there you can, in fact, then predict future excavation stages or other case histories in similar soil profiles. So what is this neural network thing? Is it a black box? Well, somehow. But let us look at the origin. Where does it come from? It's actually modeled, patterned after our neurons. And the way we learn, that is, they can adapt, they can learn. They are nowhere as powerful as our brains, but they have attributes that can tremendously benefit us. And they can adapt. And so it's a soil model that will evolve, will change, and will learn. And so you're probably thinking, prove it. Well, hang on there. So first thing we worked with, and of course I have to go back to my roots, which is Boston blue clay. We had, and thanks to accessibility of access to data from Professor Andrew Whittle, the Stata Center on the MIT campus was a well-instrumented site where they had a very good also handle on the construction history as well. This is a typical profile there that we have, and it's something that we're familiar with in Boston, and this is the over-consolidation profile at the site. We had the information also on the construction history. We had the west wall, and then we have the east and south wall sections, and they had different construction sequences. And so what we said, okay, so let us see if we can learn the behavior on one of the sections and see how well we can do on the next section. So this is the measurements on the west section, and then we started our learning process. So what we did is we trained the model initially, that neural network material model, to represent elastic behavior at a small strain range. Then as the learning process continues, which is we use lateral wall deflections and surface settlements in this algorithm, we let the model do whatever it wants. And probably those of you who work with inverse problems, you're thinking uniqueness. What happens there? Do things go haywire? Well, let's look at that. So as we introduced additional stages, the estimates improved until we got something that matches pretty well the observations. So we said, okay, so it did a good job on one section. Can it do a decent job on the other section where we have a different construction sequence about the same soil profile? So we took it there, and then we looked at that, and actually it gave us pretty good estimates of the surface settlements and the lateral wall deflection. I didn't try to get a perfect match because I think it becomes less believable. We just did it. This is the best value. This is what we got from our analysis. So then what is this neural network constitutive model? What did it learn? Did it learn something that is reasonable? Now, we've done a lot of evaluations of these type of models and what comes out of them, and you can find that in several of our papers, but I'm just going to show you and to illustrate that once. So this is a 2D model, so we need to look at plane strain data, and I think Professor Ladd knows this data very well. This is the measurements on responsive soil in Boston blue clay, a plane strain test for over-consolidated and lightly over-consolidated soils and normally consolidated soil. When we started this iteration, the model we started with is this light line here. And you can see we are completely off relative to the actual behavior. So now we let the model do its thing using the measurements from deep excavations, and we get a model that is much closer to the measurements in the lab. We did not use a single lab test in our model. We just used the boundary measurements of lateral wall deflections and surface settlements. And then we obtained a soil behavior that is quite reasonable vis-a-vis lab data. Now that's really important for us, and that has a lot of potential for us, and I'll talk about that later on. So now we have this new tool. We need to think about different ways of using it. Often enough on a project where we have a lot of instrumentation, we lose our instruments. They get damaged, the workers accidentally cut cables, damage markers, etc. We have a lot of these accidents. Can we utilize this tool to compensate for missing data? So what we did, we used the TNEC site, well instrumented, it's in Taipei, Taiwan. And we had measurements of wall deflections as well as inclinometers behind the wall, as well as surface settlements. And we wanted to use this self-sim algorithm to learn the behavior. This is before we started any learning, to show you the mismatch between the initial model and the data. And this is where we initialized it using linear elastic behavior over a small strain range. And so we said, well, why don't we just use wall deflections only in this learning process and see what kind of estimate we have for deformations elsewhere. So think of these as quote-unquote predictions elsewhere. So this is we use our wall deflections down to stage 3, and then we look at how we did elsewhere. Well, for SI1 is okay. We're underestimating here. We're not doing very well here. Not that great. And surface settlements are okay. Not great, but okay. So you can see, even with wall deflections, we did a pretty decent job, but we're still off. Now we said, well, suppose I have the inclinometer and also at the wall, and then another inclinometer, this inclinometer at distance. Suppose these were the only 2 instruments I had. How well do I do elsewhere? So I use that in my learning, these 2. So this is not a prediction. This is you're learning that behavior there. And we look at how we did elsewhere. We're doing better. We're still doing a little bit overestimating here. And we significantly improved our surface settlement. So we used 2 inclinometers to get a very good estimate of our surface settlements. You may be concerned a little bit about here. It could be due to 3D effects. And we'll talk about 3D in a minute. So from this study and also some theoretical studies, we found that using these learning techniques, we can compensate for some missing instruments. So now when we're thinking about our instrumentation program at the site and the redundancy, we can bring in also our computational tools as well. So computational tools are not just to sit there out there and you do them either before or maybe much later, but they can be part of the construction process. They provide us, we find also that inclinometers at the wall and at some distance provide us important information about small strain nonlinearity in the soil. Very valuable piece of information. We also, based on our study, we found that bracing loads can significantly enhance our estimates of deformation. So it's really good. We didn't demonstrate it yet with a case history, but based on a theoretical study. So now you say, great. So you can now do a better job at one site. How about you do a job, how about I have a different site in the same city? A slightly different stratigraphy. Am I going to still be able to do a good job? Well, we have a site, which is TNEC, where we learn the behavior. And then we have a site 2 kilometers across, Formosa Center, and we wanted to see, can we estimate the data at Formosa or the observations at Formosa given what we have at TNEC? Well, this is the site stratigraphy. You can see they are different. They are similar, same formations, but at different depth. And so we could take the different soil models that we developed for the various layers from the inverse analysis at TNEC and then use them in Formosa and see what we get. So this is the observations. Top is TNEC, which is what we used to learn. Bottom is Formosa, which is what we're trying to, quote unquote, predict. This is our learning. We learned this information there. And now we just use it as is to estimate what happened at Formosa. different construction sequence, slightly in different stratigraphy. And this is what we get. Really good data. I checked multiple times with my student. This was done by Abdurreza Usuli. I think he's probably here as well. And it was just quite impressive that we can learn. Our models can learn and learn in a flexible way. So this is all 2D. How about 3D? All this 3D geometry that we talked about. Can we benefit from that? Can we learn from that information? Well, this is back to the Ford Center. And we had some inclinometers there. These are highlighted here. And we wanted to use those 3 inclinometers in our surf learning simulations. Fortunately for us is we've done laser scanning. We have a very good record of construction, where the berms are, where the struts are. And we developed an algorithm whereby we can take the 3D laser scan and develop a finite element mesh. You see, now we're using that to close the loop. And at the time when we were doing that, our computational capabilities were limited. So we selected some of the stages, not the weekly scans, not all of them, and we used those and represented those in our finite element mesh. And then we started our learning process. Again, we initialized our model to be linear over a small strain range, and then use the data, this is the data is in dashed line, to learn that. And then after learning, using these 3 inclinometers, we got a pretty decent match. We don't capture some of these sharp edges, and I will leave that for a later discussion. But we have a pretty good estimate. Now, we wanted to see how well do we capture settlements. We didn't have very good measurements of settlements, but Professor Finno had developed semi-empirical equations for estimating deformations around the 3-dimensional deformations around excavations. So we use those estimates as our so-called measurements. And what you're seeing in the solid dashed line, this is before our self-sim learning. So we did not use this in our learning. We're doing here a prediction of those settlements. And this is what we get after our learning. We actually get estimates that match the empirical data. So that gave us confidence in what we have been doing. And also, we looked at a couple of other sides of the excavation. You notice here that the settlement trough from the empirical relation is symmetric, but ours is not symmetric. And that is because there's a difference in elevation, ground elevation, one side of the site relative to the other. And that shift is expected. We don't have it embedded in the information there, but in the empirical equations, but we can capture it in the model. But nevertheless, the estimates are quite consistent and gave us significant confidence in our modeling capability. Okay, so are we done? No, by no means. There's a lot to be done. One thing is next generation automated sensors. There's a lot of work needed there. We need much more robust sensors that will work under the water table and will not really have trouble if they are exposed to water. And they can work in aggressive environment, including stray currents. Urban areas can have stray currents and can really throw off your sensors. We need something that can do that. They have to be also cost effective, and they need to be stable and over many years. It's not sufficient. There are many sensors that will work well for a month or two, but try 3 years, 4 years, and you'll see the challenge. The other one is big data. We hear a lot about big data. We have big data, and we're going to have more data than what we currently have if we know how to manipulate it. We have a lot of image data and video, both still and video. We need ways to process that. We're seeing pervasive sensing. Are we going to just acquire the data and just simply store it and not use it? How are we going to use it properly? Do we need to be selective in our recording and the use of data? Can we automate that via some smart algorithms? We need tools to sort this data and present it in a timely fashion. That's important. And then we have the challenge of data curation. As civil engineers, our structures last 50, 100, 100 plus years. Don't we want that data to be available later on? Especially if we move everything to digital, all these records that sometimes we find of some of the bridges hidden somewhere would not exist. So we need a way to curate the data. And if you think about our digital age, it's significantly shorter than 100 years so far. So we have a major challenge. How do we curate this data? Then the issue of soil model development and how do we integrate our laboratory testing. Currently, the process we have is we go to the site, get the samples, test them, and then try to find parameters that would fit well for a model. Or sometimes we send our graduate students to develop a brand new model and then use it in a boundary value problem. Can we short circuit that process? Well, can we use the same self-learning framework and use it to directly develop our soil models? And actually the answer to that is yes. We have one PhD done and another one on the way to demonstrate that you can directly go from a lab test into a soil model that you can use in a boundary value problem and solve a problem. I can short circuit that process, but there's a lot of work needed in that. And this is where now we're talking about integration of our laboratory testing with our modeling. Bring those together. And last is drones. I think many of you have been hearing a lot about drones. They had a lot of bad rap. And just 2 weeks ago, I decided to go out on the Bay Transit Center site and explore a drone. For those of you who are interested, it's an AR drone 2.0. It has 2 cameras, one front, one bottom. You can control it from your smartphone. And you can have a GPS unit on it. You can program it to go around the site, take an image of the site. So now if you remember in my 123D catch, I had areas where I couldn't take a picture because I couldn't be there, or actually it's hazardous. I'm not allowed to be there. Well, I can fly my drone there. It actually caused quite a ruckus. I had lots of people around me watching us fly this drone, and it's really promising. It is tremendous. Everybody was upbeat about it, and so who says that geotechnical engineers don't use the latest technology, including drone technology? And that brings me to my conclusion. Our challenge in urban areas is to control deformations around deep excavations because we need to develop our underground space. Often we're dealing with marginal soils, soft soils, and we're trying to control and limit those. So I talked to you about a number of technologies that will help us in that process, in enhancing our observational method using a number of tools that represent some of the latest in technologies: 3D laser scanning, image reasoning, 2D images, 3D images, drones. Talked about network and wireless sensors and the challenges we have with these sensors. And then also our self-learning models that have a different way of looking at how we model soil. Maybe we look at developing sort of personalized soil models or region-specific soil models that will benefit, truly benefit from available data and learn that. Now, all this technology should not have us forget the basics. It is not a substitute for good engineering and judgment. It is not a substitute for detailed field exploration and laboratory testing program. And with that, thank you very much, and happy to take any questions.